All right, so we're almost done with chapter 3. This is an assortment of problems that I find amusing, and some of them are difficult. I sent you 2 difficult problems. I hope you have thought of it, because it's pointless to, I suppose, solve them right in the class. I'll just go through the solutions. So first problem, I think it's from the textbook. It's mathematician likes to drink his tea with rum in the following manner. He fills up 1 full glass of tea and another identical glass full of rum. And then he takes a sip from one of the glasses, and then pours the rum until the glass is full again. Thoroughly stirs and take another sip and continues to do so until both glasses are empty. The problem is to figure out what's the probability that the very last molecule that will be consumed, or the very last sip that will be drunk, is that entirely consisting of tea and nothing else. Okay, so naturally when I take a sip, I take many molecules, but what we are assuming in this problem is that we are sampling 1 molecule without replacement, right? So we sample a molecule from the tea glass and then replace it with a molecule from the rum glass until nothing is left. Yes, and the question is, what's the probability that the very last molecule to be consumed is that of tea? So because I have tons of questions, I will actually just go right away through the problem, right? So let's actually see the experiment containing only 3 molecules of tea and only 3 molecules of rum. Yes. So what happens is that first sample, what you do is you want tea to survive. So let's just focus for a moment on the probability that molecule 1 survives. Yes. And the probability that the very last molecule to be sampled is that of tea is either 1 or 2 or 3. So it's 3 times the probability that molecule 1 survives. Are you with me, guys? Yes. Naomi, you were petrified. All right. Good, guys. So what happens then? First sample, what's the probability of surviving first sampling? Can you tell me? First sampling means I remove 1 molecule from the tea glass, and I want 1 to survive. What's the probability of surviving first round? Please type in the comments. Great, Naomi. Glad you're back. So again, what's the probability that molecule number 1 survives first sampling? Simple question. Rainy day. Not in the mood to think today.
Do we assume that 1 survives? Or no?
Well, we are trying to calculate the probability that 1 of those molecules will be the last sampled, either molecule 1 or molecule 2 or molecule 3. So the probability that a molecule of tea will be last sampled is 3 times the probability it's molecule 1. So the way to solve this problem is to focus on the survival of this molecule through all the sampling to the very end. Yes. So then if it is to survive all the sampling, it has to survive quite a few, right? So what's the probability it is not removed? What's the probability I don't drink it right away? It means what? There are 3 molecules. It must be not the one picked. So it is what? To survive first round. That's to be sampled, Naomi. Yes. So to survive, it is 2/3. It must not be sampled. So you see the molecule stayed here. It survived the sampling, so it was 2/3 on the first sampling, and then 1 molecule from the other glass is replacing it. Notice I colored them green because I do not care what are the other molecules. I'm just focused on this molecule number 1. Now, to survive 2 rounds, it's 2/3 times 2/3. Do you agree? And then to survive the next round, it's again times 2/3. And it's 2/3 all the way until I remove all the molecules from the second glass, nothing to replace. From afterwards, it is another 2/3 and 1/2. You understand? So here is what's happening here. T is either, if the last molecule removed is T, it's either 1 or 2 or 3. And so the probability that the last molecule is T is 3 times the probability of one molecule being removed, this one molecule, yes? So that's 3 times first survival probability is 2/3. Second survival probability is 2/3. Third survival probability is 2/3. Fourth, now there is no replacement afterwards, right? So now we run out of replacements from the other jar. Next probability is still 2/3. Next is 1/2 because there is nothing to replace the molecule. Altogether, it's 2/3 cubed. You understand, guys? Woke up? Are you woke? Is that the word you're using? Yes? Good? Make sense? Great. Glad, right? So what would have happened if I had 4 molecules in each jar? What would have been the probability of molecule number 1 surviving if I had 4 molecules in the jar? We can do that experiment, I suppose, through a whiteboard, right? So you can actually devise set theoretic notations, but let's do it this way. Here is one jar. Here is another jar. There are 3 molecules of T. 4 molecules of T, I'm sorry. So it's 1, 2, 3, and 4. And of rum, also 4. What's the probability that this molecule here survives to the end? Okay, Alejandro, good, right? So let's see what happens slowly, right? Just so you all understand. First sampling, it must not be sampled. You understand? If this molecule is to be the last to be consumed, it must not be sampled, right? So then first survival is 3 out of 4. You all see that? 3 out of 4 is first survival. Now, one molecule here was removed and another came to replace it. Let's say, it doesn't matter which one, because, you know, that's the, you know, replenishing the molecule from the other jar. Now, what's the probability of surviving again? That's, again, you see 3/4. Given that it survives first sampling, its chance of surviving the second sampling is again 3/4. Yes. Now another molecule is replacing it, replacing the one that was removed, I mean. So again, survival is 3/4. Yes. Now another molecule comes to replace. Survival is again 3/4. Yes. Now I take the last molecule from, it replaces the one that was removed from the first jar. Now it's again, still it's 3/4, right? But now, now the molecule that was sampled, let's say without loss of generality, it was this molecule. Now there are only 3 molecules remaining. So surviving the next round is now what? Surviving the next round is?
2/3.
2/3, beautiful. It's 2/3. And then one was removed. Survival of the next to last round is 1/2. Yes. So the next survival is 1/2. So then I can see. I can see here. This thing simplifies to what? It simplifies to 1/4. Yes. This is just 1/4. And I was not interested in the survival of molecule 1 per se. I wanted to see what's the probability one of the 4 molecules will survive, right? So it's naturally, each of them being the last exclude the possibility of the other molecule being lost. Yes, so the probability of T molecule surviving to the last is simply this number I wrote multiplied by 4. So it is, as Alejandro suggested, it's 3/4 raised to the power of 4. Good? Everybody says it? Beautiful. Good. And then in general, if I have 5 molecules, what do you expect the probability of water, or sorry, of T being the last to be removed? What's the probability if I have 5 molecules in each beaker? Type in the comments to indicate understanding. Exactly, Naomi. And the rest of you guys? Okay, good, good. Melissa, great, wonderful. You all see that? Now, of course, in a jar, you are going to have lots and lots of molecules. So naturally, a good approximation will be this, right? So it's going to be in general n-1 over n to the power of n, where n is huge. So you might as well say n going to infinity. Good? That's the probability when you have many, many molecules in each jar. What is that limit, please? What's the limit as n goes to infinity of n-1 over n to the power of n? Good. Well, kind of, Shotaro. Be careful. Is it what is it exactly? Look at this thing and tell me what exactly is the limit. Probability can never exceed the number 1. Yes, Abhishek, that's precisely right. So the answer, guys, is very simply, you can remember I had a lecture about it to review calculus. You just divide the n, and you see this is 1 minus 1 over n to the power of n. And if you recall, we did this review. It's e to the minus 1. Good. So that's pretty much the probability. And here is that one of the questions I asked you to think about. So we will go over it. So a jewelry display window was shattered in some trinket store on Madison Avenue, and a shiny golden ring was stolen by one and only one of n suspects. Each of them is initially assumed to be guilty with probability 1 over n. Vasya Voronov is one of the suspects. An eyewitness testifies that she saw the thief escaping in a black car. An innocent person is likely to drive a black car with probability P0. Ratio of black cars, let's say maybe to city cars, perhaps. P0 is given to you. And then given this information that the probability of eyewitness information, is higher than initial probability, right? It makes it higher than just an innocent person being in a black car, right? Because she saw that somebody's in a black car, that makes the person suspicious. And then we have just out of convenience, we set A equal to P0 over P1 and B equal to 1 minus P1 over 1 minus P0. So the question is, let's say we have been able to tie this evidence to Vasya Voronov. So he is known to have driven a black car near the crime scene on that day. What's the probability if he's already suspected that he is the thief? Okay, how do we do that? So this is the way I thought to set up the problem. So I am going to label Vasya as suspect number n, and GK means that suspect number K is guilty for K 1 through n. Okay, so GN is specifically the last guy, it's Vasya. It's gonna be, the way I thought about it, it will be important in part B. And then I decided to label with BK the event that suspect number K has been driving a black car. Good. So then I want to calculate the probability of guilt of Gn given Bn, given that he was driving a black car. Yes. And that's very simply usual conditional probability. It's the probability of Bn given Gn times the initial probability of Gn divided by Bn broken into Gn and not Gn. Yes. So then this part is easy. So the probability that given that he is guilty that he would be driving a black car, it's a bigger probability. It's P1. You understand? That's the evidence is more likely because it's more likely that the guilty person was driving a black car. This way we can figure it, right? And then the initial probability of guilt is 1 over n. There are n suspects, so it's 1 over n. Same thing happens here. And then here we have what's the probability that he was driving a black car? What's that noise? Yeah, okay. Are you there, guys? So what is this part, right? So the probability that he is driving a black car given that he is innocent is just that he is an innocent person driving it. It's P0, yes? And the probability of innocence is n minus 1 over n. Good? And so what I do next is I can, of course, cancel out all the n's. So that's why you have the n minus 1 here. And I can divide by P1. Dividing by P1, I get 1 on the numerator, 1 plus what you have here. Here you have P0 over P1, which we label as A. Good? So A is a number less than 1 because P1 is bigger than P0. So this part is the easy part, I suppose, of the problem. Now, here is part B, guys. And that's why I asked this question, because of part B. Now, suppose that it was investigated and not a single other person among the suspects has been driving such a car on that particular day. Yes? It's known for sure that nobody was in a black car. Nobody left the crime scene in such a black car except for this one guy. What's the probability of guilt now? Okay? So then that's why I labeled everything like this. So I'm saying it's the probability that he is guilty given that nobody else, so B1, nobody else of the suspects was driving a black car and he was driving a black car. So this is the outcome that I observed. Yes? And so the numerator is just the probability of the intersection of all those events. And the denominator is all the, beyond the bar, the probability of those events. Are you following me so far, guys? I mean, I see unusually few people today. Yes, everything's clear so far? And then this is what we do next. So let's look at the numerator. What is the numerator? I can use this product law, right? Remember that I can condition successively. So it's probability of Gn, probability of B1 given B1 complement given Gn guilty, right? And onwards. Good? You understand? I just used the multiplication rule for probability, which we learned I think two lectures ago. You all see it. So the probability of Gn is 1 over n. The probability of everything else, right? They're independently. Let's say those people don't know each other, and independently they will drive or not drive a black car. So that means they're innocent and they're not driving a black car, right? So that means 1 minus P0. How many we have? We have n minus 1 of them. So it's 1 minus P0 to the power of n minus 1. And this is the last part is he is not innocent, Vasya is not innocent, and he is driving a black car. So that's where we have the P1. Yes? So I get this type of expression. Now here for the denominator, I used, remember this generalized Bayes formula, right? So what is true is that this event, we want this event, and we want to intersect it with one of them is guilty. So it's either G1 or G2 or G3 or G4 onwards, right? So one of them is guilty. Good. So we have this summation. And here I break it apart. So we already calculated above what happens if Vasya is the guilty person. That's the nth G, right? So I just put it here. And then here we have the summation from K1 to N minus 1 of GK, where K is not N. So I'm considering this outcome, but where the guilty person is not Vasya Voronov. Good? You follow me, guys? I hear the static of the ventilators of my computer. You can do it. Am I clear, Naomi, or am I not clear? Clear? And Valeria, do you understand? You sure? Well, okay. All right. And you, Shotaro.
Where do we get the 1 over n?
This part?
Yeah.
Because there are n suspects, and if they are equally likely initially to be guilty, one of them is guilty, right? So the probability that an individual suspect is guilty is 1 over n. If I have 5 suspects and I don't believe any one of them is more guilty than anybody else, they're equally likely to be guilty. That's 1 over 5. Yeah.
And then the 1 minus p naught is like the probability that like all of them are innocent. That's why there's the
careful.
p naught, right?
It's a p naught is the probability that I observed an innocent person riding a black car. So in other words, given that the person is innocent, I imagine, in other words, I take the collection of all innocent people and I see which of them drive black cars. You understand? So I just look at my sample space is all innocent people, and some of them drive red cars, some of them drive blue cars, or some of them don't drive cars at all. And I just want to know how many of them drive black cars.
Okay.
Right? So P0 is the ratio of innocent people driving black cars. Maybe how do you estimate it? Perhaps you see how many black cars are available in New York and how many people drive them or something like this, right? You can figure out how to estimate it, I suppose, right?
Yeah.
Yeah, good. So that's P0. And then what did I observe? Where does the 1 minus P0 come from? It means that, let's say that, I look at person 1, at suspect 1, and I observe he is not driving a black car, right? So he is innocent. Let's say I observe that suspect 1 is innocent and not driving a black car, which means it's 1 minus P0. That's the likelihood of that observation. Make sense? Yes, and that's how I calculated this part. And then here I have I'm gonna assume. So you see, I broke it up. I broke it up on person 1 guilty, or person 2 guilty, or person 3 guilty, right? And then this is the situation for Vasya that I calculated already in the numerator, and the remaining sum is where guilty person is somebody else. And then I simply see by symmetry, right? This situation is symmetric. Is it person 1 or 2 or 3 guilty, right? It's a symmetric situation. So I see that the sum can be replaced by n minus 1, and I can assume that person 1 is guilty, right? So this is probability here. All those events by symmetry, is it G1, G2, G3, all the way to Gn minus 1 will create symmetric probabilities. So it's n minus 1 times the probability.
And is it G1 just because you can just choose anything and it doesn't really matter?
Well, almost anything. You see where the symmetry breaks? There are complements all the way except for Bn.
Yeah.
Right? So for Bn, I do not see symmetry. But if I say person 1 is guilty, or person 2 is guilty, or person 3 is guilty, all the way to person n minus 1 guilty, the probabilities are going to be the same based on this information. Yes, there are of course simplifying assumptions, whatnot, right? But let's say so. So it's n minus 1 instead of the sum, and I can say G1 instead of just an arbitrary GK. And then I can condition this one, right? What is this? This is something I can solve using the multiplication rule. So it's probability that G1 is guilty times the probability that the person is not driving a car, a black car, and he's guilty, right? Blah, 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 all the way times the probability Bn minus 1 not guilty, and all this information from before. And the last thing is that the Vasya person is driving a black car, and of course he is not guilty, somebody else is, yes? So then how do you calculate it? Let's look at it. 1 over n is for this probability. This probability is 1 minus p1, right? That's the probability, the guilty person. So in other words, I look at the sample space of all possible guilty people and what cars they can be driving. If a person is guilty, what could be the cars that they are driving, right? That's, let's say, reliability of the witness, so to speak, right? So 1 minus p1 is this number. And then the remaining numbers are 1 minus p0 because they are innocent people not driving a black car, and another innocent person, Vasya, is driving the black car, so it's p0. So that's the expression that I obtain. And so this is my formula. You see it, guys? And when I simplify it, I just divide by 1 over n, 1 minus p0 to the n minus 1 p1. When I divide and simplify, I get 1 over 1 plus n minus 1 a times b. Okay, so that, because a times b, if you think about it, a times b is a smaller number, yes? It's because b is smaller than 1 and a is a smaller number. So this probability, this number here is smaller, making the fraction larger. Okay, so this probability now makes it much more likely that he is guilty. Of course, depends how many n is, how many n suspects we have. Good. So the more n suspects we have, the yeah. Well, it's actually a pretty complex relationship here. You can see b is 1 minus p0 divided by 1 minus p1. So that is what matters. All right. So you afterwards, you guys, you are aware, of course, where the exam is posted, and you are, of course, aware where you can find my lecture notes, right? So you can afterwards look at it, but try to solve this problem on your own. It's not as hard as it seems. Of course, you might think it's a little, you know, there are probabilities that are, let's say the problem is truly estimating P0 and P1, especially P1 is difficult. So here is a slightly less difficult question, but I think pretty interesting one. So here is the question, guys. Let's see what you think of it. A kidney study is looking at how well two different treatments, treatment A and treatment B, work on small and large kidney stones. Here is the success rate that was found. Here is your table. Okay, guys, everything is already seen in the table. Okay, so this is treatment A, and this is treatment B. Yes, so you can see with treatment A, it was, you see, there were 350 trials for each of the treatments. Treatment A is 78% effective on the sample here, and treatment B is 83% effective on the sample. Yes, so in other words, based on this calculation, if you calculate probability, if A is the event that treatment A is successful, calculating probability of A will produce 0.78 roughly, right? And calculating probability B, the treatment is successful, will produce 0.83. And the question is, which of those treatments is the better treatment? You look at this table. Thank you, interpret. Oh, you've heard of it. If you want, you see, understand, everything is actually calculated for you, but you can actually carry the calculations if you don't believe them. So you can condition on K or not K, treatment A and treatment B on K or not K. Thank you, Abhishek. And thank you, Sandy. Interesting. You see, because total treatment A was in total only 78% successful. Treatment B was 83% successful in total, right? So through all the trials of 350 people, treatment B was 83% successful, and treatment A only 78% successful. Shotaro says treatment A again. All right, so how many more people are there? What about Alejandro? What about Chabeli, Melissa? Okay, oh my God, everybody says A. Interesting. So why not B? Why did you pick treatment A and not treatment B? Isn't it 78% effective and treatment B more effective?
But if you're going to the doctors for this, you either have, you know, small or large, and if you look at their both A's numbers are higher. So.
Yeah, my God, you see, you're so good at it that I cannot even impress you with anything, right? My God, it becomes terrible, right? Yes, you're absolutely correct. It's called Simpson's paradox, but I guess it's not a paradox for anybody who responded. Okay, so what really happens here? Why are we getting less effective results? That's what I want to hear, perhaps, right? Why am I getting a less effective total result for treatment A? Right, look at it. If I compare for large kidneys, treatment A was better. For small kidneys, treatment A was better. But in total, treatment A was not as good as treatment B. Why is that happening? Not as good, you understand what I mean, right? So the success rate reported in total for treatment A is 78%, and in treatment B, 83%. What's happening?
Is it because for like the treatment A where it says 93%, we only had 87 people, whereas treatment B where it was 87% is like 270 people. So that's going to be higher in the total count.
Yes. So let me illustrate this with, so you understood it, right? Treatment A is better. and this is called what do you call this thing? It is, yeah, it's called Simpson's paradox. And then of course I go on a rant, right? Why did I use the letter K, right? Small kidneys and large kidneys. It's because in German it's kleine Nierensteine. And of course, since I'm making remarks, you should all read Three Comrades by Erich Maria Remarque. He's a very famous author. Two English-speaking friends that I have, it became their favorite author. They already even read more books by him than I have. He's somehow no German, I think, read anything other than possibly All Quiet on the Western Front, which in my opinion, that's not his best book at all, by a long shot. That's not at all a reflection of him, right? So do consider, you say, look at it, do consider reading Erich Maria Remarque. He is not famous in Germany, but very famous in Russian speaking, or yes, you know, Valeria knows, right? And of course, I am well aware how far you progressed in Dostoevsky, yes? And you are now reading Kafka's The Castle, Das Schloss. Now back to the paradox thing. Here is what might happen. Imagine that we have two students, student A and student B. And student A is better at solving both very difficult math problems and very easy math problems, right? He's better than student B at each category, right? So what can I do to make student B appear better than student A? I can give student B, maybe this is the only way it can be effective. If student A is not as good at solving the hard problems as student B is at solving easy problems. You understand? Imagine, let's say, you know, I take my worst student and I ask him 1 + 1, 2 + 2, right? And I take my best student and I give the best student Putnam problems, right? Probably the Putnam problems, it's much harder to answer them. So he's gonna fare worse with the hard questions as the bad student is going to fare with very easy questions, right? And so I can create, here is what I mean, right? So probability that A is successful against a hard problem is less than the probability that B is successful against an easy problem. You understand? That's the condition that I need. And then I just, what I can do is I can vary the probability. I can vary how many hard problems I give, right? So P sub A is how many hard problems I give. So if I make P sub A go to 1, I make the probability of P very similar to the probability only dealing against hard problems. You understand? So for the Simpson's paradox over here, I can make treatment A approach 73%, right? The worst it can fare is 73%. In other words, if I make it, supposedly if I just make all the stones only hard stones, right? So here you can see 78, but I could possibly reduce it as close as I want to 73. And the other guy I can increase as high as 87. You understand? Treatment B, I can make successful at most 87% of the time. You understand? Because what I will do is I will just feed, only give Dr. B, I will only give this doctor the easiest patients with small kidneys, with not small kidneys, with small kidney stones. Small kidneys is not nice. Good? Make sense? So it's going to be, because what it is, guys, what is this thing? It's a weighted average. You understand? This is just an average between one conditional probability and another conditional probability. So I will want to make the easy problems almost invisible, and then the weighted average is going to be heavily skewed to this probability. That's essentially what's happening. Clear? You understand that that between the two conditional probabilities, I can make one more important or another more important by by gravitating to one or another. Good. That's really what's happening. Is that treatment A had to face a harder challenge. So that's why I mean, what to take from it, guys, is that I want you to work obviously in this class, because That's what bothers me. I have experience that happened many times, is that by average, the better student sometimes is receiving a worse grade than a very bad one, right? It happened many, many times, right? And that always leaves me with a heavy heart. So for this class, nobody feels nervous, correct? And you're just excited about the probability. Nobody's traumatized. You just want to solve problems because they're interesting, right? And because you might do something else with them later on, like maybe read about quantum mechanics, right? It's probability and functional analysis. I can mention which book I'm reading. If you're interested, you can join, we discuss it. So here is the other question, right? Pretty interesting as well. Under ancient Jewish law, if a suspect on a trial was found guilty unanimously, then the suspect was acquitted. Good. That was reasons to acquit the suspect. So why would that happen? Why would that be a law? So suppose that we have n judges and they're deciding a case, and the suspect is assumed to be having probability P of being guilty without the trial, without new evidence presented, without all this information. Yes. Now, whenever there is a trial, there is this natural thing, you might think about recent events, right? There are certain situations that you are absolutely certain that it will not be tried fairly, right? And yeah, because people are just, they are not able to control themselves, or they respond, they see something and they right away feel in information that they don't have. Like you are seeing me, and you imagine I have legs, but all you know is that you see this torso, right? If you imagine, if you would be surprised if I stand up and there is not legs but a medusa or something, it should not scare you at all, because that's logically possible, right? I stand up and there are tentacles there. That's absolutely reasonable. Good. But people don't think this way. You imagine I have legs, or I imagine that I exist and whatnot. So that's the situation. So this is something called systemic bias, right? In every trial, it's possible that a person is not tried correctly, is that the person is convicted just by sway of emotion, that people are assuming the person is guilty, but not the justice, in other words, is not blind, right? It's supposed to be blind. It's supposed to judge without any prejudice, just based on evidence. So maybe the defense is incompetent. So there is some probability S that there will be a systemic error. And let's assume that when a systemic error occurs, then the judges will unanimously decide to convict, right? So there's something that is systemic error. The judges don't like this particular person. They right away want to convict this person. So let's say that we are going to assume that whether a systemic error occurs is independent from the suspect being guilty or not, right? It happens. Just this person might come on a trial. They're just not feeling well. All the judges, all of them have high blood pressure or something, right? And they just want to be over the trial. 12 Angry Men, if you haven't watched the movie, it's a good movie. Watch it. Very relevant. So then let's see where we are. Okay, so that makes sense so far, right? Systemic error, that's why the letter S is used. Now, if a systemic error does not occur, the probability that the judge will judge each judge independently will convict the person with probability C. C for convict and C for correctly convict. You understand? Given that the person is guilty, evidence will be presented in such a way that the probability for this particular suspect is estimated to be probability C. Yes? Don't be sad, Valeria, right? It's just a symbol pushing. Good? Now, if if the person is innocent and there is no systemic error, the person might still be wrongfully convicted by each judge independently, and we are assuming this is W. W is wrongful conviction, and we're assuming that the judges are somewhat competent, so the probability of wrongful conviction, in other words, the person is innocent, but and there is no systemic error, then they will imagine well, they will judge fairly, and the conviction rate of each of them is less than 1/2. And the conviction rate is more than 1/2 if the person is guilty. You understand? Because they are judges. They're supposed to know something about guilt versus innocence, right? Good. So then here is the problem. Suppose that exactly K out of N judges vote to convict, where K is strictly smaller than N, right? Given this information, let's estimate the probability that we have a guilty suspect. Good. You with me, guys? It's a bit complicated, but I figured interesting enough because I like this type of weirdness, right? And also lots of symbols. So here's how I decided to solve this problem. So suppose that CK is the event that exactly K out of N judges convict, and J sub I is the event that judge number I convicts. Okay, and B is systemic bias, event that there is a systemic bias, and G is the event suspect is guilty. Okay, so I have those this notation. Make sense, my notation? So I'm able to speak about each judge individually. And so what I first want to solve in A is the probability that the suspect is guilty given that exactly K judges out of N voted to convict. Okay, so what we are assuming is this, guys. Not everybody voted to convict means that there was no systemic bias. Okay, that's actually, ridiculous, but let's say that not everybody voted to convict. That means that there's no systemic bias. That's what we're assuming, right? Because they only convict, basically, if there is a systemic bias, they all convict. You understand how we reason? If there were a systemic bias, each judge would have convicted. So since not all of them convicted, that means there was no systemic bias based on that logic. Good. So what do? We then recondition, right? We just write probability that K judges convict given guilty, probability of guilt, same thing. And here K judges convict given the person is innocent, probability of being innocent. Now let's look at it, guys. Given that he is guilty, right? There's no distinction between the judges that we make, right? They're N choose K choices of exact judges that will convict. So I might just take this probability that judge 1 through judge K convict, and the remaining judges do not convict, and that he is guilty, and I multiply this by N choose K for all the other possible combinations of judges that decide to convict. So then I look at this. I can use multiplication. You see, this guy is just the conditional probability. I can use multiplication. It ends up being C to the K, 1 minus C to the N minus K, means that K convicted correctly and N minus K judges acquitted incorrectly. Good. Are you following? And then the probability of CK given that the person isn't guilty, that just means, again, N choose K, times WK, K of them convicted wrongfully, and 1 minus W to the N minus K rightfully acquitted. Good. And then, of course, when I divide, the NK's, N choose K disappear. They can cross them out, and I get this probability. Good. That's probability of guilt. This is probability of innocence. Make sense? It is, by the way, I remember, Chabeli, you asked me about binomial theorem. That's actually binomial here, right? It's binomial with conditioning, somewhat kind of a problem that can be also presented later on in the class. I hope you understood this calculation. Have you? Hello, guys. Have you understood the calculation? Yes? All right, some of you have, I guess others haven't.
So the first one you calculated, given that the person's guilty, which, how many of the judges convict them?
Yeah, so since they are K judges, I can say by symmetry, I can add all the probabilities, judge 1 through judge K, or judge 2, 3, 4, all the way to, K plus 1, or, all sorts of combinations. Because the probabilities are identical, because there is symmetry, I just say it's the same as N choose K multiplied by the probability where judge 1 through judge K convicted and the remaining judges did not.
And the other one is just the probability that the person's guilty.
The other one is symmetric. It's just now I assume innocence, so that means that whenever they convict, it's wrongful.
Okay.
Right? So here, whenever they convict, if the person is guilty, whenever they convict, that's just, and here it's wrongful. That's why it's correct and W, right? W for wrong, C for correct. Good?
Yeah.
And then I have this calculation. When you go home, guys, it's a pretty good exercise. You can, in some sense, I don't know how, it illustrates the idea maybe, right? Because it's too rigid, of course, to indicate a real chord, but it indicates the rough idea of why you want the situation. Now for part B, are you with me, guys? For part B, now suppose all n judges vote to convict. All of them voted to convict. What's the probability the suspect is guilty? Okay, so that is this information. So probability of guilt given everyone voted to convict. Good. So what is that? I skipped a few steps. So that's the probability of GCN and divided by CN, and then I can intersect with bias and no bias. Are you following me, guys? Do I need to say more? I have a feeling I need to say more. Yes, you're not understanding what I'm talking about. So here we have probability of guilt given that n judges convicted. Yes. Now, what is this? This is the same as probability of guilt and n judges convicted divided by probability that n judges convicted. Yes. So this is a bit difficult to calculate. So let's say, look at the numerator. I can further introduce bias or no bias, right? So then I say that this probability guilt and judges convict with bias plus probability guilt and judges convict and no bias. There was no bias. There was no systemic error. Make sense? All right, and then I can work with those. Now with CN, I will break it into 4 pieces, right? So probability of CN means probability of guilt and CN plus probability not guilt and CN. Yes? And then I can further break each of them in bias and no bias. Make sense? Because each of them is now going to break into further 2 pieces, systemic bias in the trial or no systemic bias in the trial. Good? Are you following me? So that's what I wrote over here. And I just kind of wrote it quickly, right? Numerator, denominator, and then I begin calculating each of those pieces, right? So the denominator contains all 4 pieces, numerator contains 2 of those 4 pieces, right? So then let's calculate guilt, bias, CN. I can always rearrange the intersection to be more convenient for me, right? So that means probability of guilt times probability of bias given guilt times probability of all judges convicting given guilt and bias, okay? So what is this? First probability of guilt is my initial P. Probability of bias given guilt is just probability of bias, which is S. And conviction is 100%. You understand? They will all convict as soon as they see bias. Doesn't matter guilty or not. As soon as they're biased, this probability is 1. So this part is P times S times 1. Clear? Now what about this? Probability guilt, not bias, and all judges convict. That's probability of guilt times the probability of there not being bias given the person is guilty. It doesn't matter guilty or not, probability of there not being a bias is 1 minus S, right? Either there is systemic error or not, and that's 1 minus S. And then the probability of conviction given guilt and no bias means each judge makes the right decision. First judge, guilty, probability C. Second judge, guilty, probability C. So it's C to the power of N. That's this part. You understand this calculation? And then I continue with the remaining calculations, and they are very similar. Here they are. Same idea, you understand? Just think about it. When you go home, perhaps solve this question. It's an interesting problem. And then you get this probability, guys. Once you factor things out, you get this probability. Good. And now observe, if you have many judges, that means n is a big number, that this part is almost zero. So if you have many numbers, the n is big, many judges, then s plus 1 minus s times c to the n is essentially s, and s plus 1 minus s times w to the n is essentially s. So in the limit as n goes to infinity, it's ps divided by ps plus 1 minus ps. And then when you simplify it, what do you get? You get p. You see, because it's ps, p plus 1 minus p times s. So that's just probability. This is just 1, so it's just probability p. In other words, the probability of guilt has not been increased at all, right, by the trial, which means the trial, it's a mistrial. You follow what I'm saying? And when do you have many judges? That's, of course, when you watch too much TV. That's when you have quite a lot of judges. Sounds familiar? And another thing, of course, is you wonder about the converse, right? If, let's say, if a person is not being tried, right? If there is some evidence or some criminal activity and the person is not being brought in front of court, and then you wonder, does it make him guilty? Should that you can calculate? What do you think? Does it imply that the person is guilty? Like, you know, you had the Teflon Don in New York, and now you have other things in New York, not just only the Teflon Don. You know who was the Teflon Don? It was Gotti. I forgot it. You don't know about your mafia? There was this guy, and you know, he was wearing very expensive. You just check for this person, right? Gotti, I think his name. You can figure it out, right? He was all swag and dressed very well, and you would always be getting into trials. I think Giuliani actually was one of his prosecutors. You know, he used to be a mayor, right? And yes, and one time this Gotti got into a fight with some guy. The guy was injured and went to the police, and there was a trial against Gotti. And then this guy, of course, I forgot. I don't know if it was this guy or not. So they called it in the newspaper, I forgot it. Right? So if you think that you are living in different times, think twice. All right, guys, here is another one. Let's see how cold and unfeeling and unimpressed you are about this problem. So let's say I actually entertained a little German boy. I wanted him to be here, but he slipped away. So you have 3 cards, right? One card is colored black on both sides. Card number 2 is colored black and red. Card number 3 is colored red and red. Yes? And here is what's going to happen. Are you with me, guys? It's pretty cool. Maybe you're not impressed anymore, but we're going to pick one card at random and place it on the table. And here is the game, right? I will win $1 if I can predict the other side. So let's say I place it I take a card that you placed on the table, and let's say I see red on top, right? And I will bet that the other side is red. And you will bet that the other side is black, right? And if I win, then I get $1. If you win, you get $1 from me. Who would you rather be? Would you rather be the guy that bets that the other side is black, or the guy that bets that the other side is red? You understand what I'm saying? If I place the card and I see black, I bet that it's black, black. If I see red on top, I bet it's red, red. So is there an advantage to me or no advantage? That's my question. Does it make sense? Does it matter if I bet red, red or black, black, depending on the situation, or I can say mixed color? Because you see, you have 2 possibilities, right? If one side is red, that means it could not be card number 1, but it could be card number 2 or card number 3, 2 possibilities, right? So does it matter? Kind of like this, yes, right? So you understand the game, guys, right? I'm showing you those cards. The card, we're going to shuffle and pick a card. There are three cards. I'm just showing you two faces, right? There are really only three cards. I will pick one of those cards and place it on the table, and then you see what color is on one of the faces, right? So let's say if the color is red, I will bet that both sides are red. If the color is black, I will bet both sides are black. And your bet is that it's the mixed card, red black. Okay, you are going to bet always that it's this card. Let's see. Okay, Naomi, thank you for, and let's see what is, so, and thank you, interpret. Let's see a little bit more of you. Abhishek, great. All right, anybody still thinking, or you want the solution? Okay. Anyone still wants to work? If you do, let me know in the comments. Otherwise, I will proceed to my explanation. Okay, sure. Okay, Sandy, great. Thank you. Perhaps I will surprise you still. We'll see. Great, thank you, Chabeli. Okay, guys, let me show you how I thought about this problem. Okay, so the strategy, well, let's understand the strategy this way. Suppose that R is the event that upturned card is red, and I want to calculate the probability that it's the third card given that I see red. Right? It by symmetry, it will be perhaps the same if I see black. Yes, perhaps at least, right? So then I calculate the probability. I can reverse it. Probability of seeing red given card is C3, and probability of C3 divided by probability red given C3 plus red given C2, probability C2, because C1 is impossible. If I see red, then C1 is impossible. I didn't bother including it, right? So here is one thing that I do. So probability of red given C3, there is no, I obviously will see red, right? Because no matter which side it's placed on the table, I will see one here. Similarly, this is one, but probability of red given C2, let's for a moment call it P. We said that selection of the card is random, right? If placement on the table is also random, then P is equal to 1/2, yes? So most of you assume that placement on the table is random, which is 1/2, and that would be 2/3. Then if it's 1 plus 1/2, I just multiply by 2, it's 2/3, and that's the standard solution, right? So it's true that it's, in other words, if your strategy, if you use the strategy 2/3 of the times, you will win the game. So some people, not you, I suppose, but some people assume that there are two possibilities, possibility C2 and possibility C3, right? So, and because there are two possibilities, you imagine it's equally likely to be one or another. Good, but that's not the situation. However, I can make it 1/2. I can make P equal to something else, right? So for example, yes, I say if the person is looking at the card and knows what the card is and places it on the table with some malice perhaps or something else, then in general it's 1 plus P. Okay. If there is no malice, it doesn't matter which side is placed, equally likely, then it's 1/2. Okay, so I introduced the possibility because, you know, I come from a place where you expect bad things from every corner. So I place P in general, right? So my solution is 1 plus 1 over P. And in the special case where P is 1/2, in other words, there is no preference which side is being used, it will be 2/3 as all that replied suggested. Here is another way to see this, right? So it could be, for example, here is my example of a bias. Let's say I know that Jennifer is looking at this card, and I know that Jennifer really does not like red because maybe it reminds her of blood. So that means that she would always want the red part to be on the table, to be covered, and the black part visible when that's around, right? So then, for example, in that case, I know that if I see red, right, that probability is 0, right? In other words, I would always, if it's C2, I will never see red because she has a choice between black and red. She would pick black facing up, right? And then the probability would be 1, right? Then I'll be certain even, right? So I understand that's what I mean by bias. But if the card if there is no bias, the card is removed and one side is selected. Another way to see this, guys, that relates to the, remember, did I mention that that sample space, right? So here is another way of looking at it with restricted sample space. So imagine that each side has a tiny label. Maybe each side is labeled 1 and 2. So like here, I labeled it black 1, black 2. In other words, this is side 1, this is side 2. Usually the number is not written, but you can imagine it's maybe under a microscope, it's possible to see it, right? Each of them has side 1, side 2. So then why is it 2/3 if there is randomness? Because if you're seeing the event red, you're either witnessing the card R2, B1, in other words, the second side of the mixed card, or you're witnessing the non-mixed card, but you might be witnessing side 1 and side 2 is invisible, or you're seeing side 2 and side 1 is invisible. So you can see that there are 3 equally likely outcomes. That's using reduced sample space, if they are, of course, equally likely, right? And then the probability is 2/3 of C3, because that's the event C3 in that sample space. Make sense? That's me working with reduced sample space and assuming that there is no bias which side I'm seeing. So seeing red, it's like that thing with the dogs, remember? Do I see the old dog or the young dog or the girls? Remember that I showed you the problem about the two girls. Are you seeing the older girl or the younger girl? So here, am I seeing red number 1 or red number 2, right? Do you want to do one more problem, or they're similar, or you kind of want to have a go? So the next one is similar, and that's, you see, look, I spent some time drawing you the prisoners. It's about who is going to be executed. So do you want to do the problem today, or do you want to keep it for Wednesday? Okay, somebody has to leave. Then I guess let's do it. Let's finish the lecture today. And if you have questions about exam or anything else you'd like to tell me, right, then stay with me. Otherwise, have a good day. Take care, guys.
I have a quick question.
Yes?
One more question about the exam, about the first problem on the exam.
Okay, so I'll stop the recording and we can discuss the first problem.
Okay.